can define it. This is now what he wrote. No, sorry, I'm wrong. This is 2 omega tilde, sorry. So 2 times omega tilde is, oh no. This is true. In, and this is now 0, 1 over E of okay, then just like this one, beta. And then he actually said that phi xi, the same phi, is defined. No, sorry. Phi beta I is xi. Where now the beta is 0 to here. I forgot. Here the alpha has a value between alpha to omega 2. Yeah. I mean that if the x goes from 0 to 1 over e, the beta goes to 0 to omega tilde over 2. Okay? So we take an inverse function this way. But now consider this as a complex value. Xi. Because just forget this. So what he did is, for real alpha from here, you can define some function here. And also for the purely imaginary part, you can define this one. Now, he really wants to define alpha plus beta I. Okay. So far, he just used this infinite integral. But now, because Euler already proves that the so-called addition theorem, so he can use this theorem as follows. So now let us introduce another functions, and this function is given by, he used as a odd notation, but okay. Then for real alpha, because of the Euler's result, we have this kind of equalities.
That's the definition.
Proof, very straight proof, is following. So just consider this as a function in alpha and beta. And so say, just take this as a, how to write it, maybe g of alpha beta, something. The function of alpha and beta. And what I will do is just take a derivative of alpha Okay? It's too complicated, so I didn't want to give it. But in his paper, he calculated very carefully about this. Yeah, this is basically it's only the function in the phi alpha. So, and of course, the differentiability is, of course, that is guaranteed because of the definite integrals. Okay, just take an inverse function. And he also found that this is completely the same as beta. That's just calculation. And then he concluded, therefore, G is originally this function, but this is just a function in G plus alpha, alpha plus beta. He concluded that. It's a little bit rough conclusion, but basically, yes. Okay. And then you know that. So this is some functions. And if you make beta equals 0, then G alpha is our original phi alpha.
So what is G alpha plus
This is
beta? What is G alpha plus beta? Because
no, maybe it's
why?
not.
So
So maybe better to say G, yeah, small g,
Okay,
yeah, yeah, right, yes. And then, so just take a beta equals 0. So if you make a beta equals 0, you can show that this part is the 1, and this becomes a phi alpha is 0. I already erased, but phi here is 0. And so this is 0, this is 1. So what you get is f beta, this is 0, so just phi alpha. Okay? So this implies that G should be phi. Therefore, this theorem holds. That's his proof. Of course, that's already that Euler shows that this formula. So once if you know that this formula, then it's not so difficult.
in 18th century, it's normal.
Yes, but actually, the Euler has really difficulty to find out this formula at the beginning. It's a real calculation. Okay. And also similarly, this is rather complicated form, but also I will show that it's the same similar formula hold for f and large f also. Just take the partial derivative with respect to alpha and beta and show that both are equal, so that the right hand side is a function of alpha plus beta, and then if you make beta equals 0, then it goes this way. Okay, so this be careful, this is originally only defined by alpha plus beta is inside of here. Okay? But I will use this equality, okay? I will use these equalities to define alpha plus beta I. So this is the only value, real value, but just assume that this also holds for the. So for example, what does it mean? So beta I is actually the definition now. So 1 plus c square e square and phi square alpha, and then here phi square beta I, and here phi alpha, and f beta I, and f beta I, plus phi beta I, and f alpha large f alpha, and so on. So you can also define assuming that this addition formula always holds, so that you can extend that the region of alpha and beta further and further. So it's a modern terminology. What he is doing is sort of the analytic continuation of the Melonic functions. And actually, you can show that. Why does Abel did succeed is phi and f and large f is in a sense analytic functions, so that it's even if it's only defined on the real values, actually you can extend a little bit to the complex neighborhood, so that this can actually really hold. But this is an afterthought. So Abel didn't know such things, so he just assumes that this addition theorem hold for the complex case, so that to extend it in gradually. And then you get very, very interesting things. First of all, this has sometimes 0. Why? You must check. Phi alpha, no. This is 1 over c. Okay. That's just inverse. And also, phi to omega tilde I is I. So in here, denominator becomes 0. Okay? This is minus of 1 over e square. And this is 1 over c square. So 1 minus 1, so it's 0. So this is not the function defined on the complex plane, but there's some pole. In the modern terminology, it's some pole. So it's some point you cannot define that function at some point. Just checking very carefully about this addition theory that phi of alpha plus 2m omega plus 2n omega tilde I, okay, m and n are integer, is equal to phi alpha. Okay, so that means that if we change this argument to some integral multiple of 2 omega and some integral multiple of 2 omega tilde I, then you get the same value. So here, the first time, people know that there is a periodic function and whose period, 2 independent period, because 2 omega is real and 2 omega tilde I is purely imaginary. So for example, the sine function, cosine function is it's a periodic function, but its period is just a multiple of 2 pi. Yeah? But in this case, it's similar, but 2 directions it has a period. That's okay? Or? So what I will do is just writing that complex plane. So you have here some 2 omega and here 2 omega tilde